In this lecture, we'll deal with the concurrency. Before I move on, we'll deal with the basic concept called thread. It's a new abstraction for a single running process. A program can contain multiple threads. A multi-thread program has more than one point of execution. So it means that a single process or single program can have multiple program counter. And the threads in a program share the same address space. And as we switch context between processes, we also switch context between the thread. So each thread has its own program counter and a set of registers. And one or more thread control blocks are needed to store the state of each thread. So this is, in process, this is struct process control block for a process that contains the state of the registers used by the process. Let's say process control block for process. One or more thread control block are needed to run a multi-thread program, and they are needed to store the state of each thread. So when switching from one thread to another, from T1 to T2, for example, the register states of T1 is saved, and then register state of T2 is restored. And the most important part, address space, remains the same. So the page table base register or CR3 register, CR3 register does not change. This is a very important part of the thread. So when we switch the process from one process to another, we have to save and restore the address, and also we have to change the page table. However, when you switch the threads, we do not have to change the address space, and we do not have to change the page table. We can keep using the same address space. That is a very important part of the concept of threads. So a thread share the program and the heap. However, each thread has its own stack because each thread can have its own local variable. So this is a single thread address space, and this is an address space that has two threads. So there are two stacks, stack 1 and stack 2. The two threads share the program code, which we call text, and they share the heap. Why do we use threads? There are two reasons. First one is parallelism, and second one is I/O. In parallelism, let's consider two CPU system, and we are multiplying 4x4 matrix, and then we are multiplying 4x4 matrix. This is 4, this is 4, and this is 4, and this is 4. If you use two CPU, then you may want to write a program that performs matrix multiplication in two pieces. First one, let's cut the first matrix into half, part 1 and part 2. And then CPU1 is responsible for multiplying this matrix to matrix of part A. And then CPU2, this is CPU2 and this is CPU1. CPU2 is responsible for multiplying the second part, B, and multiplying it to the rest of the matrix. In that case, we can expedite the matrix multiplication process. With single thread, you cannot do this. But if you use two threads, then individual thread can perform matrix multiplication on different CPUs, and then when they are done, the result of the matrix multiplication can be coalesced together to form a result. So in this type of program, multi-thread program is natural and typical way to make the programs run faster on many core or modern hardware. So parallelization is a task of transforming a standard single-thread program into a program that does this sort of work in multiple CPUs. And multi-thread is used to avoid blocking program progress due to slow I/O. For example, if you consider a web browser, for example, you open up a certain web page, and then in a certain web page, it asks you to type in your user ID and password. And it waits for you to input your user ID and password. But if you look at the web browser, then there are lots of other programs running, like updating the time clock and music's playing, and Adobe Flash image is keeping updated. So as you can see, even though a single one of the thread is waiting for you to input your user ID and password, rest of the part of the Chrome browser or web browser just running fine. So multi-threading enables the overlap of I/O with other activities within a single program. This is sample code. This is probably the first code you will see, and this is for how to create the thread. This is for creating the thread. Okay, there is a function. Name is myThread, and it prints a string supplied by the caller. And there is main program, and you see two functions called pthread create. Here, apparently, these two functions create two threads, namely thread P1 and thread P2. And then each of these functions are executing its own thread, and it is called, name of the function is myThread. And then the caller passes string A, and caller passes also string B to this thread. This is how you create the thread. And then there's another function called pthread join. So in this line, caller waits for P1 to return. And then after it returns, it waits another pthread P2, and it returns for P2 to finish. And then after two threads completes, the caller prints main. So this is actual code for thread creation. Okay, so let's enumerate the possible execution scenario of creating a two thread. First one, main function starts to run, and it prints main begin. And then it creates two threads. And then it calls pthread join and waits for T1 to finish. And then because it blocks, and then context switch happens, and thread 1 starts to run. And thread 1 starts to run, and it prints A and returns. And then it waits, and then the main thread, the caller for wait function, returns, and then it calls another function, pthread join, for T2. And then because the caller has been blocked, the context switches to thread 2. And the thread 2 runs print B and returns. And then the thread 2 finishes, and control returns to the caller, and it prints the main. So in here, the order in which the strings are printed is A, B, and main end. This is another scenario of running thread 1 and thread 2. First, the main starts running, and then it prints main begin. And it calls pthread create, and thread 1 is created. Right after thread 1 is created, somehow the operating system transfers control to thread 1, and thread 1 starts to run. And then it prints A and returns. And then after creating thread 2, the control is also transferred to the thread 2, and thread 2 starts to run, and then prints B and returns. And then the control is transferred to main program, and then main program calls pthread join for T1. Because T1 has finished before, it returns immediately. And then it calls pthread join for T2. It returns immediately because T2 has done already. And then it prints main end. This is another scenario of creating and running thread 1 and thread 2. The main function starts running. That prints begin, and then creates two threads. Somehow, operating system decides to run thread 2 first instead of running thread 1. So it runs, and it prints B and returns. After it returns, the main function calls wait for T1. T1 has not started running yet. So after switching the context, thread 1 that has been created starts to run and prints prints A and returns. And then after thread 1 finishes and returns to the caller, the main function calls wait for V. This line, waiting for the completion of T2, returns immediately because T2 has been done before. So finally, it prints main end. The interesting thing is that the order of the print statement here, this is executed first, and then B gets printed, and A gets printed, and then it prints main end. So the order of printing A and B is switched in this scenario. I'm going to explain the concept of race condition. Consider a statement of increasing value variable by 1. It says counter is counter plus 1. So there is CPU and there is a register. And then we are increasing the value of a condition variable counter, and not condition variable, just counter by 1. This is the EAX register. And so the first thing we have to do is read the variable which represent counter from memory to register and increase it by 1, and then save it back to the original place. This is the process of increasing a value of a variable by 1. So details of the instruction look like this. There is move instruction which loads the memory variable to the register and increase the value of a register by 1, and then save the value of a register back to its original memory location. Okay, this is simple, but when the two threads competing against each other to increase the same variable, there is very interesting things happens. So there are operating system, there are two threads, thread 1 and thread 2, and they are trying to increase the value of counter by 1, thread 1 and thread 2. So this is how it happens. So let's assume that thread 1 starts to run first. So it loads the memory variable to the register, and then it increases the register value by 1. And then timer interrupt has happened and context switch has happened also. And then operating system saved the state of thread 1 to its thread control block, and then it restores the register state to T2. And then thread 2 starts to run. And then it again moves the memory value to the register, and it increased the value by 1, and it saves the value back to its memory location. And then timer interrupt has happened again, and then thread 1 starts to execute. Thread 1 executes the last instruction move, which saves the register value of EAX to the memory location. Well, this is plain and simple, but let's look at actually what happens in the memory. Let's say thread 1 executes the first instruction. Okay, at the beginning, the counter variable is 50 and register value is 0, and after move, EAX register contains the value 50. And then it increased the register value by 1, so the value of EAX register becomes 51. And context switch happens, and then thread 2 do the same thing. It loads the memory variable 50 to the EAX register, and then increase the EAX register value by 1, and then saves the 51, the EAX register value, to the memory. After resuming from thread 2 to thread 1, thread 1 saves the contents of EAX register, which was 51, to the memory. So after executing thread 1 and thread 2, the counter value becomes 51. But thread 1 has increased the counter value by 1, and thread 2 has also increased the counter value by 1 as well. So from our perspective, the counter value has increased twice. So the final value should be 52, not 51. but somehow the memory contains 51. So this is called race condition. There are a few terminologies. Race condition is the situation where the result of an execution depends on the timing execution of the code. The problem of the race condition is the result is indeterminate. And there is another important concept called critical section. Critical section is a piece of code that accesses a shared variable, and the critical section must not be concurrently executed by more than one thread. So only one thread should be allowed to execute the code in the critical section. So if multiple threads executing the critical section, then it can result in a race condition. So we need to support atomicity for a critical section, and it is called mutual exclusion. The ideal approach to execute multiple instructions atomically is make the increment as a single assembly instruction, like this. But this is not an easy task. In general, we do not have such instruction. Instead, we use lock. Following code ensures that any such critical section executes as if it were a single atomic instruction. So there is a statement that increases the value balance by 1, and it is wrapped by the function lock and unlock. And then we can ensure the atomic execution of critical section.